So it's a great pleasure to introduce Dr. Lawrence Tratt, who is a reader in the software development group at King's College London. So Lawrence has been working in the area of virtual machines, and in particular, since we're using virtual machines of all kinds every day in every app we use, it's really important to think about exactly what's going on in there. And he's going to tell us today about things that are happening in virtual machines that we didn't know and we probably don't want to know.
Thank you, Ben. I think that's probably a very good summary of the whole thing. Right, so we're talking particularly about programming language virtual machines here, just to disambiguate. We're talking about things like the Java virtual machine and all those sorts of things. And a lot of the work here is done in collaboration with these fine people you see on the front. Towards the sort of second half of the talk, I'm going to give you some sort of personal opinions and thoughts, which these guys may or may not want to be associated with. But yeah, the whole point of this is that we're normally people who develop and use VMs to do things, and here's where we looked in things a bit more detail and found some outcomes that if you're a VM developer are probably pretty depressing, but it's okay because they kind of depress me too. Now, what do we expect in the performance from VMs? There are a lot of claims made about VMs, but I think this summarizes everything really neatly. So I'm not picking on Cliff particularly because he's one of the giants of the field. So he's one of the people behind Hotspot, the main Java VM. He's a giant of the field. He's captured the notion of what we tell developers really clearly, which is, in this case, he's saying the Java virtual machine brings GCC minus O2 to the masses. And we have a pretty clear intuitive idea, I think, about what that means. GCC minus O2 makes C code run fast, so the VM must make code run fast as well. So on the surface of it, it makes a lot of sense. But what's it actually referring to? So let's imagine that I have a benchmark, and I'm going to run the benchmark in a loop, and I'm going to put each iteration of the loop on the x-axis, and I'm going to time each iteration on the y-axis. What might we expect the performance of a VM to look like? Something like this, I would suggest. So the performance, the VM's going to start running the user program in a profiling interpreter. It's going to look at the program and work out which parts are most frequently executed. It will then decide those are worthy of compiling, and we may expect execution to slow down a little bit whilst compilation happens. And that's okay, because eventually we hit the nirvana, the happy state of peak performance. All of the numbers that we ever see about VM performance are given in relative to peak performance. This is the thing that VM developers love, but it ignores everything that comes up before it, the warm-up phase. Yes, sir?
Java VM do the profiling at the beginning? I thought that they just JIT everything, like C#, no?
No, well, it depends. I mean, there's several JVMs, but if you look at Hotspot, it's got an interpreter, and then there are Java VMs that immediately convert to machine code, like Maxine was one that did that. But even if they have that, they'll still generally have tiers, because you can't compile everything to efficient machine code straight away. So you do a quick job, look in more detail, and then do a better job later in one way or another.
Yeah. Does C# do it differently? Like,
I don't know. That's my.
I was expecting it to do something similar.
I don't know if C# emulate instructions. I mean, interpret it.
So I'm completely ignorant of this.
What C# does is typically they're just JITting, and so they have to choose a less aggressive optimization strategy. They just JIT from the start with no profiling. More advanced VMs do profiling and then repeatedly up the level of optimization as they find that something's hotter and hotter.
Yeah, and we will probably expect to see multiple tiers.
.NET JITs all code?
It just JITs all code.
Okay, all right.
And then, the compromise is it does affect your startup performance. And the other compromise is you have to limit the kinds of optimizations you do. So doing very aggressive optimizations is generally not possible in that kind of scenario.
Yeah, agreed. Well, and we'll see some sort of black box numbers that I think will back up that view in some of the other VMs. So I'm going to apologize straight away because we didn't benchmark any of your VMs.
That's okay. The data will hold true. I think what's considered the state of the art for VMs.
Yes, yeah, probably. So this warm-up thing, that's the time between the program starting, executing, and it hitting this peak performance. We thought it would be kind of important, right? Users always notice warm-up. They complain greatly about it. Most of the complaints you see about VM performance are because people either didn't understand or didn't appreciate warm-up, or it's a bit longer than they expected. So we thought, wouldn't it be interesting to know how long warm-up takes? So I asked Ed and our team if he could just maybe do a quick experiment, just it would take a couple of weeks as my estimate, and 3 person-years later, we have some results. We eventually embarked upon this big experiment to measure the warm-up of various modern language implementations. And because we're trying to be all scientific, we even made a hypothesis. Now, I'm going to warn you in advance, the whole experiment is biased to make VMs try and look good. So we're deliberately biasing that way. So our hypothesis is really very easy, one would hope, for VMs to satisfy, which is if you take small, deterministic programs, the VM should simply reach a steady state of peak performance. We're not saying it's going to be fast or anything, but just that that should happen. So a very simple thing for it to do. Then the next thing is what benchmarks to use. So this is an incredibly fraught thing. But for us, unusually, we can use the language shootout benchmarks, and they're perfect for us for 2 reasons. 1, they're small. 2, every VM has looked at them. So we know that every VM has checked that they work well. So no one can accuse us of using benchmarks that are weird that they haven't thought about. So that's good. The first thing we had to do is make sure the benchmarks are actually deterministic. One of them had a random seed that's not reset on every iteration, so we fixed that. In Java, lazy class loading is occasionally visible to a user. And we checked that just by putting print statements around if statements and while statements and so on to see where non-determinism happens. So we got rid of all of the non-determinism that as a user can be observed. And as you'll see, we have benchmarks, the same benchmark in various language versions. So we have checksums that are the same in every language version. So we can roughly check that each language, the benchmark in each language is doing the same job. And we also use the checksums in a certain way that makes it very hard for the JIT compilers not to remove the whole benchmark, which if you're not careful, they tend to do. So we kind of make it harder for them to cheat. How long should you run a benchmark? So I know from my own experiences in VM, there's all sorts of magic numbers inside. And the magic numbers can be 10, 16, whatever, but it's quite common to have magic numbers that are 1,000 or 1,024. For obvious reasons, we love those sort of numbers. So we wanted to run our benchmarks for more than 1,024 iterations. So the for loop that runs the benchmark must be more than 1,024. So we chose 2,000 because my maths tells me that's bigger than 1,024. So there's some thought behind that number, but we didn't know exactly how high to go. We then shut down the VM and we rerun the VM 30 times, what we call process executions. We had no idea what a good number for that was. That is frankly pretty much pulled out of my rear end. We had just no idea what to do there. So the top number has some thought, the bottom number, who knew? And then we have various VMs. So I won't bore you with all of these in detail, but just to give you an idea, Graal is a next generation JIT compiler for the JVM. HHVM is Facebook's PHP VM. Truffle Ruby is a version of Ruby that uses Graal on the JVM. Hotspot is the standard Java virtual machine that you would get with OpenJDK. LuaJIT, I suppose, is fairly obvious. PyPy is a fast Python virtual machine. V8 is the JavaScript VM in Chrome, and GCC is not a VM. It is a static compiler, but it serves as a baseline that we can sort of get some sense of comparison. The first thing that we try, yes, sir.
Can I ask just a quick question?
Yeah.
So, I'm trying to remember the numbers, but V858, I think, is when they were in their old, we JIT everything with a low perf change,
Correct.
and they just switched over to
Correct.
now Interpret Plus.
Yes, they've moved over to, so I can, are they now in Crankshaft and Turbofan, whatever the code names? Yes, yes. We keep updating this, but they're all moving targets of one description or another. So the first thing we did to try and make the experiment as reliable as possible is we used the same version of GCC to compile all the VMs. So were we to see any odd effects, they can't be because we use Clang to compile one VM and GCC or different versions of compilers. So we removed that as a variable. And we also wanted to get some sense of what is the effect of different machines and operating systems. They must, something must be going on, but we didn't really know. So we had 3 machines involved. Linux 4790 and OpenBSD 4790, those are both i7 processors. They are, to the extent that we could determine, because we ordered them from the same manufacturer, the same machine, except we got the amount of RAM wrong in one of them. But apart from the amount of RAM, they're the same machine as far as we can tell. Linux 4790 and Linux E3-1240 v5. The E3-1240 v5 is a Xeon processor, so the 2 Linux machines are running on slightly different hardware. So we're going to get some vague idea of different hardware affecting things and some notion of what happens if you change operating systems on the same hardware. Then we did a lot of the standard things that we all know and love we should do when benchmarking. We turned off turbo boost for obvious reasons. We actually found undocumented intermediate modes on some i7 processors in turbo boost, which was highly entertaining. Hyperthreading, no one knows what the effects of it are, so we just thought, no. We turned the network card off, so whatever state actor is currently disliking us will not try and spam our machine and spin up our SSH daemon or whatever. And indeed, we disabled a lot of other daemons like cron and SMTPD. Because those things can run occasionally and interfere with things. And there's so much of this that we had to write a new benchmark runner, which we called Crumb. The K in Crumb is a little tip of our hat to a guy called Tomasz Kalibera, who'd done the best benchmarking methodology we'd previously seen. And what Crumb tries to do is control as many of the confounding variables as possible. In other words, it tries to control the experiment so that there's less likelihood that external factors are messing around with things. Yes, sir?
So with the hyperthreading, I mean, isn't one of the things that people do push off JITting to a different thread?
But one of the all of these machines have 4 cores, so there's several cores.
They can use a different core anyway. So it's not about multiple cores. It's just about the fact that they use the hyperthreading within a core.
And then hyperthreading the hyperthreads interfere with the normal cores in ways that are very hard to reason.
So that just normalizes.
Yep. So I'm not going to go through everything Crumb does. You'll be very glad to know, but I'll give you a few hints of what it does. One thing, it doesn't do any I/O while benchmarking is happening. It runs every VM with fixed memory sizes, stack sizes, and so on. Every time a process execution happens, it deletes a Unix user account and recreates it, including deleting the home directory, so there can be no cache files between runs, which VMs can do. We reboot the machine before the first and after every subsequent process execution. So if a VM somehow pushed the machine into swap, that can't affect results. After every process execution, we check a bit in the process. Did the CPU overheat and was throttled? If so, we rerun that process execution. It doesn't happen often, but it does happen. Maybe, I don't know, like 0.5% of the time, somewhere around there. We know temperature affects the machine in various ways. A processor, obvious one, but we don't know what else. Maybe RAM chips get throttled. I don't know. So we check the temperature, all the temperature sensors in the machine when we run the first process execution, and we don't run subsequent ones until they're pretty much back at that point. We don't know the effect of that, but just to make sure it's not there. And there's a whole load of other things that it does. It goes into a lot of detail, as you can. Yes.
Is this available somewhere?
Yes.
Want to recreate this?
Everything is open source. Everything is available. This is it's fairly Unix tied, if I'm honest, at the moment. For some bits of it, you can use a custom kernel to get even more features, but you can run it on a pretty stock Linux machine and get most of the effects. And it's all relatively well documented, relatively. Ben?
I'm curious if you try to evangelize this to, because anybody who's running performance measurements could benefit from this. And there's a lot of papers that do that, right? Mm-hmm. So have you been trying to convince people? I mean, is it catching on?
We've not directly tried to convince people. I would like to think that people might be convinced having seen it. But often people look at it and go, that looks like quite a lot of effort.
You've done the work. Right?
I know.
The only one I would take issue is automatically rebooting the system, because yes, for what you're trying to avoid caching or behavior of the VMs.
Yeah.
But it's possible that what people see in practice on a system that's been running for a long time differs from what they see in practice on a system that is freshly run. So there is some variability possible that you
absolutely. And every time you reboot the machine, it doesn't quite get back to the same state as before. We're trying to be at least a little bit clever. So when Crumb loads, it has a sort of a to-do file. That to-do file is a fixed size so that it only ever allocates exactly the same amount to run before a process execution. Afterwards, it can do whatever it wants. So we try and remove it a bit, but you're right, you can never do a perfect job. And you've always got some compromises.
So this is a great list.
Yeah.
So.
There is more on there if you want, but let me show you some data. We've got, yes, sir.
Emery Berger has this thing called stabilizer.
Yes, and stabilizer is an indefinite influence on a word. So for those of you who don't know stabilizer, it's a way of running C programs. It uses Clang. It statistically runs programs and reruns them with the statistical guarantees that it's covered the random layouts and so on of a program. And the cool result from that paper, if I remember correctly, is that they show on their benchmark suite, Clang -02 is statistically indistinguishable in performance from Clang -03. So that's the core result. But I actually took something different from the stabilizer paper, which is it completely convinced me that there's no notion of a program having a performance number. that programs inhabit a set of performances because of all the various non-determinism inherent in our systems. And that's completely baked into our whole methodology, that thing. So it's been a big influence on that. And it's a really cool paper, and I wish more people knew about it. Stabilizer doesn't currently run anymore, unfortunately.
Some of this randomization as part of.
We get some of the benefits just by rebooting the machine. We get some accidental randomization, which we don't control. We have no statistical guarantees. We would like to have used Stabilizer itself, but it doesn't run anymore. Emory's looking into updating it, but I'm not sure it's been updated yet. Okay, so here's some real data. So we've got various versions of the experiment. I'm going to show you one from our latest run, which is the 1.5 run. And we're going to see lots of plots that look like this. So there's a legend at the top. Let me quickly explain that. This is the Fancouche benchmark running on Lurgit on the OpenBSD machine, and it's the 14th of 30 process executions. As before, on the x-axis, we've got the benchmark running in a for loop from 2,000 iterations, and on the y-axis, we have the time of each iteration. You'll often see we have these little zoom-ins. They're kind of based on some heuristic that allow you to see the warm-up curve, sometimes a little bit easier. And the first thing that's fairly obvious here is the program started relatively slow, got faster for a while, and then hit the steady state of peak performance. Okay, it took it 98 iterations to do so, and the wackiest people we know who've ever measured things before looked at about 30 iterations. So no one looked quite long enough, but hey, it warmed up. And the noise in the system is really quite low when you look at the y-axis, so that's cool. But we've got 3,500 of these plots per machine, so more than 10,000 overall. How the hell are we going to analyze them? So we had no idea what to do for quite a long time before we collaborated with a very clever stats lady, Rebecca Killick at the University of Lancaster, and she's an expert in something called change point analysis. And what change point analysis does is you feed in time series data, which is what we have here, and it tells you when the nature of the data is shifted. So let me visualize the change points on this particular thing. So you've got these horizontal and vertical red dash bars. The vertical bars are change points. They match our intuitive notion that the data on the left of that bar is different than the data on the right. It's the shift in performance, effectively. Between two change points, and there's an implicit one at the beginning and the end, you have a change point segment. So we have, in this case, two change point segments. We can perform classifications and statistical analyses on these change point segments automatically. Now, the change point analysis is not very fast. It probably takes a couple of seconds per run, but it's completely automated. We had to tweak it a little bit for our case because it doesn't know anything about our domain. So we wanted to make it take into account the fact we have a little bit more noise than perhaps it always would consider naturally. But basically, it's a very simple and very powerful technique to do this. Okay, so this is a standard sort of plot we see. And this is, I would claim this is good warm-up. But here's another one that we see. Now, this is n-body running on PyPy. The first thing you'll notice is this huge red dot. That's an outlier. So it's a standard thing in these sorts of analyses that when you see occasional blips that are slower, you consider removing them from the analysis. And that's what we've done here, because maybe that's the garbage collector running or something that we don't want to affect the change points and change point segments. So there's one change point segment in this example. Notice that the benchmark appears to be as fast as the beginning as it is at the end. So there's no, now I'm going to be biased here. I'm going to assume the VM has warmed up so fast I can't measure it. It's done the perfect possible job. But I've now got kind of two styles of graph, this one and this one. So I'm going to have to make a classification of different styles of warm-up. And I'm going to say slightly different words. Yes, sir?
Go back just a second.
Yeah, sure.
So I'm very interested in this outlier thing, right? Because this is something that, I see when people are like doing benchmarks, they're like, oh, I want to understand what the behavior is, so outliers aren't interesting to me. But in talking with like so a lot of the engineering teams, I think there's a big interest in, we have 95% of the time, people have great experiences on our website, and we have 5% of the time, there are these horrible outliers. So they're not like, oh, this was garbage. This is something we care about a lot, and understanding what events were going on at the time of that outlier, so they can be like, was it a GC? Was it my code? And I just was unlucky, but this is something I should fix. Was it a hardware?
So it depends on how, in our case, if there's just like the odd iteration here and there, as in this example, we just exclude it and we assume hopefully that didn't make your life too bad. If there's more of them, they will form a different change point segment. And you'll see later, then I think that's something I would completely be looking at.
And would that include even if they're sort of distributed,
no,
uniformly or randomly?
It depends how, in our case, how close they are together, whether they form a change point segment. And I agree very much with you that I would probably look at this if I was a developer to see what it is. But it's always a trade-off. We could give you all of the outliers and say you can look at these and some other data if you wanted to do so. But it's generally, you'll see some examples that I think may show you why we've done this.
Okay.
And then you can see if you agree or not.
So do you have enough sort of logging with each of these executions that you could actually drill down to why?
I'll get onto that later.
Okay.
The things you're seeing at the moment have no logging turned on because that interferes a bit with things. But we do a second experiment with that later on.
Okay.
Okay, so we've got this classification algorithm, and I'm going to say slightly simplified words to make life a bit easier. If there's one change point segment in the plot, we say it's a flat classification. If the final change point segment is the fastest of any change point segment, we say it warms up. And we consider both of these equally good, morally equivalent. We make no distinction between them. And you can see things like this. So this is faster on V8. This might be where you're seeing several tiers of compilation, for example. I don't know if that's what's happening, but it's plausible. Sort of gets slower for a while, and eventually it hits the steady state. Okay, it's taken 590 iterations, but it got there. That's warm-up. I consider that good. Here's one, and this relates to your questions about outliers. So I think these are, if I remember rightly, these are garbage collection spikes in this case. And eventually it hits a steady state, and it's got these outliers. And, I again would consider that good warm-up. You may care a lot about those spikes, but in this case, they've been classified as outliers. But still, overall, I think good. Here's where it gets fun. This is the Richards benchmark on hotspot. Now, what's a little bit difficult to see because the red lines obscured it here, but you can see from the zoom in, performance started in the top left, slow, got fast for 200 iterations, and then got 4 to 5% slower. Now, what's more fun here is the Richards benchmark was used from day 0 to benchmark the performance of hotspot. It's one of the 2 or 3 most important benchmarks in the history of that VM. It's been used forever. No one ran it long enough to spot that it gets worse performance over time. And I'll give you a little bit, some suggestions as to maybe partly what's going on there later. Okay, this isn't supposed to happen, right? So we now have to change our classification algorithm, or augment it. We say if the final change point segment is not the fastest change point segment, we will classify this as a slowdown. Over time, the thing got slower. That's not supposed to happen. And it happens quite often. So here's faster on V8, and it's got slower this time. Okay. And this is the final type of data that we see. So this is binary, I'm not picking on V8, but this is binary trees on V8, and it's continually shifting. It's never appearing to stabilize. So we somewhat arbitrarily say, if there are any change points in the last 500 iterations, we'll say that this is a no steady state. And we can't give any statistics on this other than to classify it. So that's our final type of classification, no steady state. Just to be clear, the top 2, equally good. Bottom 2, bad in different ways. You can argue amongst yourselves as to which one you consider more objectionable, but they're both bad. Now, the classification algorithm, there's always going to be a few gray areas where people can argue a little bit over what's happening. So this is, if you're a German speaker, I apologize, I can't pronounce the name, Pfannkuche on hotspot. Can you see there's a sort of sawtooth pattern? It goes above, below, above, below. Depending on the version of hotspot we benchmark, that sawtooth gets shallower or deeper. In this version, the sawtooth is quite shallow, and the change point analysis has considered that one change point segment. When it's deeper, they end up with lots of change point segments, and this would be a no steady state, whereas at the moment it's warm up. So there's always going to be a few gray areas, but mostly the automatic algorithm really does a very good job of matching our intuition, and unlike us, it will happily analyze 10,000 plots without getting bored. Which helps a lot. This is binary trees on V8 on the same machine. You run it twice, once on the left, it warms up, once on the right, it's no steady state. So you get inconsistency on the same benchmark, same machine, same VM, running the same things twice. And we see a lot of this. That's unexpected. So that tells us now, if you were just to take one of those process executions and give statistics, it's not going to give you a reliable idea about the other ones. And this is where we took inspiration from Stabilizer. Yeah, sure.
In your Crumb, so Crumb, in the perfect world, you wouldn't see this because Crumb would have controlled all the...
Well, no, because the VM may have internal non-determinism that it's for whatever reason doing that can show these numbers.
Okay, but so that's after you narrowed it. So you feel like Crumb controlled enough that now you're attributing this to the VM. But did you go through a process of adding things to Crumb that slowly got, that narrowed this down and made it more infrequent?
Yeah, I mean, I'm not going to claim that this isn't external effects because there are just so many variables that we can't imagine. But we've done our best to remove as many as possible, so it's more likely that it's the VM.
That's what I'm saying. So
Yeah.
you used to see more of this, and then as you added features to Crumb,
Yeah, actually, what's interesting, so we would like to do an experiment where we actually work out which of the features made the most difference. They definitely do make some difference, but we definitely also hit the law of diminishing returns after a while. And we would love to know what made the most difference, but it would take, months of running time.
From an end user perspective,
Yeah.
I know we're trying to understand the effects of VMs on performance here. But from an end user perspective, this is actually the thing that matters most of all is when you have inconsistent process executions on a real machine, and it's like a factor of 2 or 3 or 10 difference. So anyway,
Yeah,
I think it's great, but I also think this is sort of the problem.
Oh, no, this exactly. I just wanted to, I was assuming that you had gone through this process of seeing this a lot,
Yeah,
and then
I mean,
as you
obviously tried to
added things
pin
to
it down,
Crumb, you
but-
narrowed it down.
Yes, sir.
Do you think that this is caused by the VM or caused by the whole OS? Because if OS does something unexpected,
ASLR could do this to you,
Yep.
for example. You
Yep.
just get unlucky in your random layout.
But
So-
the variance between the different
So
segments.
that things overlap in the cache, the physical cache.
So
Therefore, you get conflicts.
So all we're measuring things as a black box, and so I'm not going to claim that this is the VM or the OS or whatever. But if you're a VM developer and want to know about your performance, these are the numbers you're using, and if you don't know there's this variance, you'd be surprised. A lot of VMs are very consistent on certain benchmarks, which makes me think it's more likely to be the VM with this weird thing than not. But that's a guess.
But why do you think a VM developer should just take one run and be done with it?
I don't think they should do that. I completely.
I mean, sorry to interrupt.
No,
We
of course.
saw this in some internal projects doing compiler measurements. We saw this kind of stuff all the time. No matter how hard we tried to control for stuff, we just could not.
Yep.
We could not get things where we considered it statistically meaningful because it's just all. I mean, it was constantly saw this.
Agreed. Ben.
So this is 2 of the 30 executions?
Yes.
So, this is obviously a lot of contrast, but was it the case that, a significant number were one way and not, this is the outlier of the 30? Or is it
Well, in this case, I can't remember. We can have a look later. I've got statistics for that.
across the 30?
yeah,
right?
yeah,
Okay.
yeah,
So,
yeah,
I was just
we'll
curious
see.
about how consistent this kind of variance was.
We would run benchmarks and we could see, and we would run the same benchmarks on the same machine for weeks at a time,
Yep.
consistently. You'd see drift and skew happen, all kinds of weird stuff.
The amount of it is kind of shocking. Yes, sir.
So, I think this is awesome to characterize the performance. Did you do any analysis of why this is happening?
I've got some suggestions for that later, although they are approximate suggestions. I'm going to give you correlations rather than causations. If I could give you causations, I'd probably be a very rich man. But
Show this to people at Google? Are they aware of this?
Yes.
Yeah.
Yeah. Have they changed anything? This, just to show that VMs are not the only problem, this is binary trees on C. So this is not a VM. On the left, you've got Linux, on the right, OpenBSD. Can you see this bouncing ball pattern on the left? We think, although we've never got around to investigating, that's the malloc implementation on C. Notice that on OpenBSD, it's massively slower than the Linux version. This is a slightly slower machine than the left-hand side, but it still shouldn't be 4 or 5x slower. What I learned from this, and this is an obvious point, but what I learned from this is we tend to think of VMs as being these massive, big runtimes, and languages like C being these incredibly sleek, no runtime things. But of course, libc, all of these things, your malloc implementation is a runtime, and it can have these sorts of effects. So we saw more odd patterns with C than I expected. Not as many as with the VMs, probably, but still more than I expected. So eventually you get these 3,500 plots, and so Sarah, who did this table, this is like probably the tour de force of LaTeX. I mean, you do not want to know what underlies this. And in answer to your question, Ben, you were asking about V8 on. Actually, I'll get back to that in a second. All right, looking at this will make your eyes hurt, right? So I'm going to zoom into this one on the bottom right, just so we can see what's going on. What we've got here is the Spectral Norm benchmark with the various VMs. Let me interpret some of these rows for you. So I'll take hotspot to begin with. This squiggle means all 30 process executions warmed up. Good. Steady iter hash is what iteration number was the steady state reached. Iteration 7, there are interquartile ranges below, but we'll ignore those. You get a little histogram here. The red bar is the median value, so you get some idea of the spread of the distribution. Steady iter s in some senses is the same measure with different units. It's how many seconds did it take to hit the steady state, 1.9 seconds. And then the final one, steady performance s, that's once you've hit the steady state, what is the performance of each iteration? So it's 0.3 seconds, and then with a confidence interval in this case of plus or minus 0.169 seconds, so a massive confidence interval. So that's interesting. But okay, at least it warmed up. If you look at Graal, all 30 process executions slowed down. It took 14 iterations and 13.6 seconds to hit the steady state, and the steady state performance wasn't great. It was a 3x slower than hotspots. This equal sign here, so on PyPy, that says this is what we call good inconsistent, which means you've got a mix of flat and warm-up, which we consider morally equivalent. So you've got 27 flat process executions and 3 warm-ups. And the steady-state performance was okay. And then you get this. This is the bad case. So when you see equals with a cross, that's bad inconsistent. That means you've got at least one no steady state or slowdown. So in this case, you had 25 slowdowns and 5 no steady states. As soon as you get a no steady state, there's no statistics we can give. We're just stuffed. Oh, there's one I missed here. Luajit, all 30 process executions are flat. By definition, they warmed up immediately, so we don't give those, and you get steady perf numbers. So you can tell, as a VM developer, you can tell a lot based on this in various different ways. And you can really start to drill down on what's happening. Now, if I start to summarize all the data across the machines, I'm going to ignore the OpenBSD column because it's slightly different for reasons I don't want to go into now. Let's look at the middle column, which is the Xeon machine, and I look at the bottom half of the table first. The way to read this is, of all of the process executions on that machine, 23.3% were flat, 43.9% warmed up. So that means about 2/3 warmed up in the correct fashion, as it were, and about 1/3 didn't. Now that's pretty bad, but it gets worse. If you look at the top part of the table, now we consider VM benchmark pairs. So the way to read this is 11% of VM benchmark pairs, all 30 process executions were flat, 17.8% all warmed up, and if I go down here, 8.9% were a combination of those two. So that means 11 plus 17, so 28, 36, 37% of VM benchmark pairs warmed up in the expected fashion. By far the biggest category is bad inconsistent. So this is where you've got one or more slowdown or no steady state. So more than half of these VM benchmark pairs sometimes slow down or have no steady states. That's bad. So let me summarize that again. Across those two Linux machines, about 67-70% of process executions warm up, about 40% of VM benchmark pairs. And if you take across both machines, only 12.5% of VM benchmark machine triples. So warm up does not happen anywhere near as often as one would expect. So, are there any simple explanations? So we have a second mode we call instrumentation mode. So we rerun things and we get extra data for some of the VMs. So the way to read this, at the bottom we've got our traditional plot in seconds. And the middle plot says for each iteration how much time was spent in the JIT compiler. And the top one is how much time was spent in the garbage collector per iteration. So you can see in this benchmark here, the performance is sort of gradually going up over time. There's a sort of slight incline, which is kind of weird. When you look at the time spent in garbage collection, it exactly correlates with the time in seconds. I would suggest there's a memory leak in the VM. We've reported that upstream. I don't think it's been fixed. Now, I'm not claiming causation. I'm only spotting correlations. But, it seems very plausible. Here is Richard. So this is the one that slowed down. And just before the slowdown happens, you can see there are a couple of JIT compilation events. Probably either the second tier compiler in Hotspot kicked in, or it just reprofiled and decided to run with more aggressive optimizations, which actually did a worse job. So it doesn't tell you exactly where to look, but at least you know it's probably something to do with the JIT compiled code. So sometimes we can see these relatively clear correlations, but sometimes you see things like this. So this is the one with that sawtooth pattern from earlier, Fankush and Hotspot. When you turn instrumentation mode on, it interferes with the timings for a while. Eventually the sawtooth reappears. But there are some JIT compilation events, but they don't correlate with the sawtooth. So I have absolutely no idea or suggestion as to what might be causing them. Just no idea. There's no garbage collection at all in this benchmark. So what is it? I don't know. I wouldn't know where to start looking. Now, that raises an obvious question. I'd say in about half of cases, we just can't see a correlation with just-in-time compilation of garbage collection. So that raises a question. How, warm-up doesn't happen as often as we think. There aren't as many simple explanations as we might hope. How did we get to this situation? It's embarrassing for my field, if I'm perfectly honest. Yes, Ben?
So one thing it seems like you could look at, I don't know if you did or not, but is if a JIT happens and then there's a change point, right? Yeah. Then you can say, well, did that JIT help or hurt? Right?
Yeah, that's true, yes.
So that's sort of like, overall, is the JIT, when it tries to do a recompilation, and I'm assuming, sort of these later ones are sort of like more optimizing, right?
In general, yes.
How often does the thing that when it kicks in and tries to do better actually do better, right?
Yeah, don't know. Good question.
Yeah.
I mean, because there are only correlations, so we'd have to be a bit cautious about saying, even though there's a JIT event just before a change point, that it's definitely the cause of it. It's probably the cause of it, but we can't be entirely certain. But I agree, it would be very interesting analysis to do. We didn't.
Because I think, too, this, so the idea of the staged JIT where you do more and more work, I think this hypothesis is it's worth it, you get more benefit, et cetera. But of course, it makes the compiler more complex.
Absolutely.
So at some level, you have to ask, is all this extra complexity worth it? And the answer is related to the fact that you want to see the benefit, right? That this extra level optimization gave you a big win, right? And it seems like what you have now is sort of a mechanism where you could actually start asking that question, right?
I agree. I think and one could dive into a lot more detail here. Yeah, I completely agree.
It's also not always the case that it generates better code.
Yes.
No, that's what I'm saying. I mean, clearly, if it slows down.
In JavaScript, it's the opposite, right? You make aggressive assumptions initially, and then as you go on, and those assumptions are invalidated, you generate worse and worse code because you're like, well,
that's
this program is kind of crazy.
Right.
Not a benchmarking person, so I'm kind of, it's maybe a naive question, but the sawtooth that you're seeing here is like out in microseconds.
Yeah. Right, so a lot of
is that traditionally interpreted as being like a significant variation?
So it's a really good question. Some of the differences we've seen have been multiple percent, and some of them are very small. But once you've got a VM to a certain level of maturity, your optimizations are generally in the 1% category. So if you see a 1% fluctuation, that's the difference between telling if you've made a good new optimization or not. And the timings are really stable within change point segments to a very, very precise degree, which I was really surprised by. So I'll give you a philosophical thought, which is that if we're observing these small problems at the sort of 1-2% level, there may be multiple of these problems hiding elsewhere that we can't spot. So that's why I think it's worth looking even in these degrees. But some of the changes are really, really big. Like you do see ones that are 10-20% occasionally.
Yeah, I mean, the argument would be if we're seeing jitter, maybe noise is just inherent in the system and people can live with a 5% jitter or something like that. Mm-hmm. Clearly, when you get into 10 and 20%, people are going to get upset about that kind of stuff for a high performance system.
Yeah, I'll offer you another thought on that later that we'll build upon that. But I think it's complementary to everything we've just said. Right, so we've got to this pretty depressing point, right? And I started wondering, how did we get here as a VM community? So I'm going to offer you a couple of personal thoughts, and you can decide whether you agree with them or not. Benchmarks, I hope, guide the optimizations of any compiler. When you make an optimization, use benchmarks to tell if you've done a good job or not. I really hope everyone does that. An obvious question is, are they complete guides to the performance of a VM, or any type of compiler indeed? So I'm going to give you a war story. Dropbox used to use extensively Python for all their server code. And they tried using PyPy, which is a just-in-time compiling Python VM, and they said, found it slows their system down. It's not very good. So they started writing their own Python VM called Piston. I bumped into the main developer of this after a while, and I said to him, what was it that caused the problem that made you, embark on this pretty significant project? And he was very kind, and he sent me the benchmark. And it was really clear what the problem was. I looked at it. It was a benchmark with lots of recursive function calls, and for reasons that I don't understand, PyPy unrolled recursive function calls immediately. Now that's really dumb. You would never unroll a for loop unless you knew it was a good idea, and you'd only do it to a very small level. So the fix was really clear for this benchmark. PyPy should not be unrolling recursion in these sorts of programs. So I thought this would be a fun little project. I've never looked at that part of the JIT, and it took me about 3 days to work out where to change it. This is pretty much the complete diff. Half of its comments. It's not a big complex change. I applied that diff to PyPy, and the benchmark that caused Dropbox to invest several $1 million in a project they cancelled last year. The benchmark's now got 13.5x faster. I code for money. So it looks like I can pat myself on the back for a job well done, but PyPy comes with a benchmark suite, and some of those benchmarks were slowed down by my fix, and I knew, quite reasonably, that the developers would not take my patch while some of the existing benchmarks were slowed down, no matter how better I'd made this other one. So clearly, I was going to have to allow some unrolling of these recursive function calls. ASCII art is about as good as I get. This is from the email that I sent to the developer list. This is not paper quality benchmarking, but it's approximate. Hexium 2 down to telco, these are the 5 PyPy benchmarks that I made slower with my commit. And the way to read this is as following. If I basically don't unroll recursion, ray trace simple gets 3.3x slower. If I unroll a couple of levels of recursion, it's 3.1x slower. And eventually, by the time I've unrolled 7 times, all of those 5 benchmarks have returned back to the same performance as before my fix. So that looks good. For reasons that I can no longer remember, this is Dropbox's benchmark, polymorphism. The timings are in seconds. I'm sure it seemed like a good idea at the time. So higher is worse here. And by the time I've got to 7 unrollings, the benchmark has got slightly slower than before, but it's still way, 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 way faster than before my commit. So from this table, then it is completely clear what to do. And the benchmark suite said the right thing to do is to unroll 7 levels of recursion. That's what's in the commit, the fix that went into PyPy that I suggested. If you download that VM, that's the amount of unrolling you'll get with recursive function calls today. I suggested that value, even though I doubted at the time, and now I'm completely convinced it was the wrong value. What do I think the right value is? I almost guarantee you the right value is 1. In other words, don't unroll anything. But the benchmark suite told me I should have 7 levels. And that's the gatekeeper to getting performance in. Because the benchmark suite is 25 benchmarks. It's as VMs go a relatively large benchmark suite, but it's still very small. It doesn't give you an overall idea of all of the possible performance that you might see in the real world. So it can give you a skew. But that's what I had to do. So, yes, Ben?
Why not add polymorphism to the benchmark suite? Because wouldn't that have, like, the benefit you got from that, the 13x, outweighed all the losses you had?
So that's a really good question. And I think in general, VM teams have a tendency to say, we don't want to make anything slower. And not always, but it's hard to say, if imagine you're a customer, got 2 customers, I'm going to make your benchmark faster and yours slower. Now he wants to kill me. So I can see why it's a really hard ask, but and we don't have a very good way, I think, of reasoning about what's an acceptable trade-off. Okay, so that's war story number 1. Right, the other way of looking at benchmarks is benchmark suites are they, in a sense, are they semantically correct? If they tell me an optimization made something better, did it really make something better or not? And again, I'll give you another war story. So Octane is, or at least was, probably the standard JavaScript benchmarking benchmark suite, originally from V8 17 benchmarks. So me being completely clueless about JavaScript, I downloaded it, and this was the first JavaScript I'd ever written, I put a for loop in that just made each benchmark run for 2,000 iterations. Nothing complex. And I ran it through the V8 on its command line interpreter, and it runs the first few benchmarks, fine, and it gets to PDF.js, and then boom. And I looked at that and thought, oh, God, what am I going to do? Until I noticed it says process out of memory. I'm like, okay, let me look at this in a little more detail. So I just printed out the timings of each iteration, and this is rough quality benchmarking, but you can see it's sort of fast-ish, gets a little slower before boom. So I just put a slightly more detailed timing information in, and then I'm going to cut off the data before this point where my mouse is, just so we can zoom in, and it looks like this. Now, I can see a pretty clear guess as to what's happening here. You can see these spikes here, and they're roughly linearly increasing in time. I would suggest that's probably the garbage collector gradually having to do a bit more work until at some point here, it enters panic mode of some description where there's so little memory left, it's just thrashing and thrashing and thrashing until boom. Right, now, it's a correlation, not a causation, but this is a memory leak if ever I've seen one. So I thought, how am I going to look through I can't remember how long PDF.js is, but it's several thousand lines long. What are the chances of me finding the memory leak here? They're about 0, given I don't know JavaScript, but I thought, I'll try. So I loaded it up into my trusty editor. I scrolled past the license, and the second line of code says, var canvas logs equals open close square bracket semicolon. Oh, that looks like a global mutable array list thing to me. I wonder who does stuff with that. So I just searched for the usage of that variable, and there is one. It says here, push something, and it doesn't really matter what that is, into that array. And it does that on every iteration, and it never empties the array. I found my memory leak in about 60 seconds. I really thought I wouldn't stand a chance. Oh, okay. So the fix took me about 15 minutes because I couldn't work out how to empty an array in JavaScript, but I eventually got it right. This is the fix. Google haven't merged this because they say the benchmark suite is unmaintained. And there was some argument about whether you empty it before or after the loop, but it doesn't matter. That fixes the memory leak. Why is this a problem? So imagine you're a VM developer doing JavaScript VM, and you think, I will make a change to my code generator. I'll try and generate better machine code. I'll use this benchmark among others to tell me if I've done a good job. This benchmark is only measuring your garbage collector in extreme conditions. It tells you nothing really about the quality of the machine code generation. So it will completely mislead you in that regard. Worse, it will also mislead you as to the magnitude of a change. So Octane, as with many other benchmark suites, can say run as many iterations as I can in 10 seconds. So imagine I can do 100 iterations in 10 seconds before my change. I make a change. Now I can do 110 iterations in 10 seconds. It looks like my change has made things 10% faster, but each iteration is doing more work than its predecessor. My change is actually quite a lot faster than 10%, but the benchmark suite is misleading me, and it's more likely to make me think that a change isn't effective than effective.
How can you decide if a benchmark is a good benchmark?
Well, okay, that's a
You could say,
deep philosophical question. I don't know. I think that in general, more benchmarks is the quantity to an extent gives you quality. So that you, rather than relying on a very small number and hoping that they are good benchmarks, by just having a lot of them, you're just hedging your bets in a nice way. That's the least worst answer I have for you. It sucks as an answer, I apologize.
Well, so, I mean, I think the spec community went through this, the C and high performance, and, in general, the community as a whole has gone through this before with spec.
Yeah.
And so you generally want benchmarks that represent real code that runs in production, that represents the scenarios. So the question I would ask, for example, is it normal that you just load this JavaScript code and then throw it away and only run it once in a browser? If it is, then it's fine. In fact, you're iterating 2,000 times is the problem.
Well, yeah, but if
I'm suspecting it's not. I'm suspecting that if you let this code run in a browser and it ran long enough and it was doing some kind of animation, it will run out of memory and crash your browser or your browser.
Yeah, indeed. And if
I mean, but I'm sorry.
No. I'm completely agreeing with everything you say.
okay.
But so the spec community choosing benchmarks for C and C++ went through this, and there's always been some skepticism from people familiar with spec when they see these like 10-line JavaScript programs. Like, what? That's not a benchmark. That's a micro benchmark.
Yeah, agreed. And this benchmark is a large one.
Yeah, this is a real. I would agree. This is a real benchmark.
I see that you have 14 slides.
That's true. That's true.
I
Okay.
should wait. I assume you have a takeaway message at the end.
Yeah, well, we'll see.
So far, these are the problems, but we don't know the solution.
Okay, so here's we can agree this is a problem, this benchmark. But if you look at Octane, it's not the only benchmark of those 17 with a problem. Another benchmark has a blatant memory leak, same problem. Another one has something that I think is a memory leak, but I'm not sure. Yes, Ben?
So just to understand, so are these intentionally in there because they have the memory leak?
No.
Okay, I mean...
In this case, it was actually extra code added to the benchmark that made it a memory.
The memory leak. I see, okay.
So we made it worse.
So that seems like an obvious fix, right? I mean, I don't understand why people would push back at all, right?
Nor do I.
Yeah, okay.
The benchmark suite uses a non-monotonic timer, so you can observe benchmarks that take less than 0 seconds to run. And many of the benchmarks run around a microsecond, so if you have a resolution of a microsecond, your timings are just terrible quality. Not good. So the problem is, this is showing you this benchmark suite is, in my opinion, relatively misleading as a VM author, and will have misled, I suggest, many VM teams. So I posted this title at the beginning of the talk: why aren't more users happier with our VMs? So my thesis, the belief that I've come to, is that for any compiler, but I think perhaps particularly so for VMs, the benchmarks that you have, the way that you go at benchmarking, determine your trajectory. They are your performance destiny. And I think ours have misled us. So I have some suggestion for what we can do to benchmark a little better. First thing is just running benchmarks for longer than we bothered doing before shows all sorts of odd problems. Very simple to do. Yeah, it takes longer to run, but it's not difficult. peak performance in steady state might not occur. So if your benchmarking assumes that, then you will be misled as well. I think it's dishonest not to report warm-up time, at least internally, because we should care about this. I think it's something users care about way more than we give credit for, and it would be better if we knew more about it. I think we overtrain on small benchmark suites. Well, I don't think it's very obvious. We could perhaps learn from the machine learning community to an extent in this regard, where they have the idea of separate training sets where you run them and get all your magic constants, and a validation set where you measure things. It's a bit more annoying to do in our situation, but maybe that would help us. This goes back to what I said, more benchmarks, more better. And I think the more the merrier. I think we're off by an order of magnitude in the size of our benchmark suites. I also have a hunch that users would prefer we tried to focus on making a wider variety of programs run quite fast than doing what we currently do, focus on making a handful of programs insanely fast. I think that we're misled ourselves by focusing too much on a few small programs. And that leads to a big question. Can we fix these problems? I mean, we saw some of these things earlier, some correlations. We have a little project from Cloudflare to look at fixing Luajit, one of the smallest VM. There are some real low-hanging fruit there that we were quickly able to do. And then we came across a benchmark that had some odd performance, and after 12 weeks, we had got nowhere in terms of fixing that. We'd ruled out a shed load of things, but we hadn't found the problem. We've actually abandoned that because 3 months of effort on one benchmark is kind of enough. And that leads me to think that I think we can fix VMs a little bit, but I do not think we can fix them all the way, because I think that the assumptions that are embedded in VMs that are often decades old, the people involved have left or forgotten about them, uncovering those assumptions is massively difficult. Once you've done that, you can probably fix them, but I think it's incredibly difficult to do. Yes, sir?
In reality, I assume we run performance monitoring on our program that's deployed on the customer machines. That is, in some sense, more representative than I do some changes, I run a benchmark in my test machine, right? So in that sense, shall we just rely on more about perf numbers collected from the field instead of worry about benchmarks too much? I'm not saying we shouldn't do it, but
no, I think that relying on real-world things is very important. But one problem with real-world systems is there's a lot of noise in them that's inherent, and it's very difficult sometimes to see what's going on. I also think, and this is a personal gut feeling based on what I see here, that imagine you give me a real-world program and it takes 20 seconds to run, or a minute, or whatever it is. The question is, I have no idea if it could run 10 times faster. We don't know what I call that the performance thing. We don't know what it is. And so we just don't know if we're doing a good job. I think that our results suggest there's a lot more performance to be had from programs. And I think in that sense, it's sometimes a little bit easier to use smaller benchmarks for something, but I desperately hope people benchmark real things as well.
JavaScript is messy because unlike Windows, you don't have you run Word and you're going to have a million people running Word and you can gather perf data and maybe develop some well. JavaScript, the code is usually generated on the fly and the libraries are sucked in as part of some web page. So I think it's very difficult in production systems to disentangle. First, you'd have privacy issues about what you get. Second, it'd be difficult to disentangle the programs, the libraries are being driven in different ways by different websites.
Agreed. Yes, Ben.
It seems like, but in the case of something like PyPy, there is a Dropbox is obviously a big player, and so making Dropbox work well, because they're probably one of the people that have the biggest, Python investment, would make sense, right? I mean, in some sense, you sort of follow the money or you follow the users, and the same thing with all the AI tooling it's done in Python. I mean, it seems like knowing the audience, right, and focusing the performance benchmarking around the people that matter is a much better story than a bunch of little things, right?
So yes, but one of the challenges that I often refer to performance problems is people don't think they have a performance problem until they do. And they normally go from not thinking they have a performance problem to having a performance problem in about 24 hours, is my experience. And then it's just mad panic. And then these sort of longer-term investments are very hard for them to do. That's my experience, and I think perhaps explains why we've not seen some of the longer-term work gone into this. So one obvious thing that we could do is if we were to start writing newer VMs from scratch and we benchmark more carefully from the beginning, we're more likely to catch these problems before they become deeply embedded. Now, the problem is I can't afford to have 50 developers working for 10 years. So I've got to do something with a smaller team, but I have an idea. It's an idea that actually some of you might be vaguely familiar with. So do you guys remember Spur, which was a VM that came out of MSR a long time ago? It wasn't called this at the time, but it's an example of a meta-tracing JIT. I'm not going to go into this in very much detail, but the idea of a meta-tracing JIT is you just write an interpreter for your own language, and you get a just-in-time compiler based on that for free. So here's a dumb interpreter, the sort of thing an undergrad could write, stack-based interpreter. Imagine at runtime I have this little user program on the right. What I do is when I want to convert that program into machine code, I record all of the things the interpreter on the left did. That's what's happening on the right. I optimize that trace, convert it to machine code. I can now use it in place of the interpreter. And it's a very powerful, very simple technique for getting quite good performance. It's not going to match a handwritten VM, but it gets probably 80% of the way there for 20% of the effort.
Sorry,
Go
I
ahead.
don't understand.
Well, so normally this bit takes about 40 minutes to explain. So I'm giving you a very, very simple thing. Can you see each instruction like that little program here? How much detail do I want to go into? When it went round to the next...
So you're basically doing partial interpretation of the interpreter.
It's kind of a dynamic partial evaluation of sorts.
Maybe we can talk later, but this is sort of like also Graal is taking this approach, right?
Graal is similar. I would say it's a cousin approach, yes. I can definitely talk in more detail about that. Right, so I'm going to run through these bits quickly. So when you look at one of these meta-tracing systems, it starts in the interpreter, you find a hot loop, and you trace it, compile it to machine code. You can now run the machine code in place of the interpreter. The machine code's clearly only valid for some program states. So sometimes you encounter a program state the machine code can't handle. You then have what we call a guard failure, and there's a system whose name I dislike called the black hole interpreter. And the black hole interpreter's job is to get the state of the machine code back into the state that the interpreter can reevaluate via a safe point. And that's how you can eventually generate all the possible program states should you need machine code for that. Yes, Ben?
So this is like a trace-based JIT, like
Yeah.
Mozilla, right?
Yeah.
They pulled it back out.
Yes, they did.
But yeah.
This one, the JIT thing is automatically derived, whereas that was TraceMonkey and that was manually written tracer.
Okay.
When you look at the performance of these things, let's say the interpreter is 1x performance, and let's be optimistic and say the machine code's 10 times faster. That tracer component that you have to get through to get to the machine code is about 200x slower because it's a software interpreter interpreting another software interpreter. The memory thrashing is beyond belief. It's horrendous performance. And why is that a problem? Well, the obvious one is you're not going to want to generate machine code for a loop unless the loop executes for at least a couple hundred times, or you won't made back the cost of tracing. But worse, you're so scared of tracing because of this cost, you put it off for as long as possible. The warm-up of these systems is not good, and it's one of the reasons I think they've often suffered a bit in the past. We had no idea how to solve this until in the last couple of generations of Intel chip, there's a feature called Intel Processor Trace, which allows you to run a binary, and you can give an arbitrary sized memory chunk and just say record the control flow the program took. So we're going to replace the software tracer with a hardware tracer. We can get that, and that has like a 5 to 7% overhead. So with our other gubbins, we think we can get that down to sort of 2x. Now, the warm-up of these systems could potentially be viable with existing systems. So that's our big idea.
So the tracer is tracing the interpreter's
we're going to
the hash code here, interpreter here, and the tracer here.
You've got
Then that means the tracer actually understands the semantics of the interpreter,
Yep.
so that you know.
So we're doing this in a Rust system, and we basically compile the Rust program twice, once with a version of the control flow we can guarantee to understand. So that's how we get around the problem. We've got about 3/4 of that middle component written, enough to tell that it's not obviously stupid, but not quite yet enough to guarantee it works.
How is this different from my interpreter is smart enough to just while I interpret, I maintain some information. Then after a while, I just say, I jump to machine.
This one's automatically deriving the tracer for you, so you don't have to write it yourself. In your system, you'd have to write it yourself, and that's going to take you a few years, probably for a big system.
They should already have it, right?
No, you have to write it manually.
JavaScript doesn't have it.
Depending on your JavaScript interpreter, it may or may not be a tracing interpreter. I don't know about the ones you have here.
I mean, one of my questions is, one of the key things for JavaScript is observing the types and the shapes of the objects. How does that work with processor tracing?
Right. So processor tracing just gives you a faster trace, but in a tracing compiler, what you do is you speculate that if you've traced something and an object was of type O, you then optimize based on that assumption, and you leave behind a guard. So if you later execute the machine code that assumption is incorrect, you'll have a guard failure.
But where do you make that observation that it was typo in the first place?
It naturally, I don't know if I've got an example here. It naturally happens inside the tracer. Here, these are guards. Okay, this is not a good example. I don't have any type checks in this one, but it's one of these guards would be a type check, and that allows the optimizer to make assumptions based going forward that naturally specialize on the object type. And you're right, it's completely the most, inlining and type specialization are the most powerful optimizations. Inlining first, I think, but then type specialization. Okay, so I'm aware I'm taking too much time. So if you want more details than you could possibly want to know, that top paper was in Uppsala last year, and it's on our website. It's got lots more details about Crumb and so on. All of the stuff I've shown you, the warm-up statistics, they're all open source. You can run them on your own VM, on your own data. You can produce plots and tables just like ours. So those where you can download them, including Crumb. We're lucky the UK government and Oracle and Cloudflare paid for this, because otherwise we would never have got this far. And with that, thank you very much for listening.
So I do have a question, which is, if you have some insight into how noisy the systems are, because a lot of the examples you showed here were in the, they were in the 2 to 5% range.
Yeah.
Do you have any insight, or is that in your papers?
We found that the real system, especially once we've crunnified them to get rid of some of the external noise, the noise level is much lower than I expected. And you can see the fact that there are often these VMs very consistently warming up with tight confidence intervals shows you that if the VM does its job properly, there's not that much interference from the OSM. One of the things we notice, which I can't really quantify, is sometimes benchmarks change core and their performance changes very slightly, consistently changes performance. That could be a hardware problem, or it may be some other things that we just don't really understand. So there are some effects that definitely slightly do weird things that we're not sure about, but my conclusion was that you can measure to a much higher degree of accuracy than I ever expected.
But the question I'm getting at is, what kind of variation are people, if you extrapolate these benchmarks or representative of real code, what kind of variation are people going to find
in real
practice?
systems? On a system that's not been sort of set up for benchmarking, you mean?
Well, even just based on the inherent, you sort of, one way to interpret your data is there is some kind of noise going on or measured across a wide range of VMs. And the question is, what is that noise? Because if I'm an end user, like I said, depending on my scenario, at 2%, it's a nuisance for the person writing an optimization trying to make things faster. Yeah. But for somebody running a high-performance computer system, it's probably like, whatever, I can live with 2% jitter.
Right, so I completely agree. I think a lot of the time, the small ones that we see, which are probably the majority of cases, but certainly not all of them, the level of performance difference is not significant enough to worry most end users. But it worries me deeply as a VM author, because it goes back to this notion of a performance ceiling. In general, I don't know how fast a program could go. So every time I observe a performance slowdown, something's gone wrong. You have several of those, and then actually maybe my program, the real-world program, could go 20% faster if I didn't have these flaws. So that's the kind of way I think about it. It's not the direct effect that's the problem, but that all of this missing power that we could have given users and efficiency. That's what I'm concerned about, or what this has led me to become concerned about.
It makes it very difficult with this noise to know whether any individual optimization is actually an optimization, a customization. Exactly. Because most optimizations in a tuned system, you're correct. You're going to get into the 0.25%, 0.5%, 1%. Yep. And the problem is for real-world systems, you'll see maybe 100 of these things matter.
Yeah, I agree.
And the question is, which 100? How do you find them?
And I think we've misled ourselves. That's my guess. Yes, Ben.
So, when this thing on the right, when you have these changes, it seems like, if you look at the same thing over and over enough times, you can find a correlation between some external event and the change, right?
In some cases, yeah.
Well, I'm just curious. It seems like an experiment to do, because you could say, well, it could be an external event, like it changed processors, but that would give you the explanation. Is it within the JIT or is it external to the JIT, right? That's causing these things.
So I don't remember for this particular case, but I am fairly confident that one is not correlated with shifts of core. So all of the benchmarks are single-threaded. The VMs may have multi-threading stuff in the background, so we don't see that many core shifts, for example.
Okay.
It's unusual to see certainly a benchmark shift cores this many times. So That's, for example, unlikely to be an explanation for that one, but it does explain the overall ones.
But you have enough information, and you could rerun the experiment repeatedly, so that you could establish some kind of causation or causality.
Yeah.
Right, where you could
I think we can often rule things out.
Yeah. Okay.
Yeah.
Okay.
I agree with that. Yeah. Yes.
So, like, have you thought about identity using perf counters? Like, maybe when they go up, it's because of cache misses?
Yeah, we don't have cache misses, but we do check some of the performance counters. Mostly, they correlate with the time in seconds. But the reason we care most about the time in seconds is A, because that's all humans care about, but B, because that includes anything the kernel does. So it's actually possible by either deliberately or by mistake, as it were, to offload benchmark work to the kernel, which performance counters don't count. So I think performance counters give you a view of performance, but they don't. They can somewhat be misleading in that sense, which is why I haven't bothered showing you that data. But we do have that data actually for every benchmark.
What do you mean by correlating by second? I don't know.
So all of these times on the y-axis are in seconds, and if you look at if I showed you the performance counter for this benchmark, the shape of it would almost exactly match the shape of the time in seconds, just in cycles.
So it means that the performance counter do reflect the increase.
In most cases, yes. Yeah, in most cases. But not always, and we felt this is the one that we care about most as humans, effectively. Yes, sir.
So it sounds like this cool technique of using the hardware to do the tracing is you were positioning it as a way of getting a pretty good VM on the cheap.
Yep, that's correct.
Do you think it has anything to say for the scenario in which the existing large VMs that people with deep pockets sort of build over many years?
Yeah. Could they use a similar technique? So I don't think they can use exactly the same technique, but I think they can use processor tracing, for example, to do things like. So this feature in chips is not being widely used yet. It's in the last 3 generations, only the last 2 generations of works. I think it was mostly intended for profiling dynamically and so on. And I think VMs could use that, say, okay, I generated some machine code, I run it for a while, then I'll use processor trace to see what it actually did and whether it will be worth me having another go at compiling. Not exactly for the tracing as we're doing, but for sort of similar but distinct reasons. And I think that could be very powerful because, as you can see from this example on the left, at the moment, VMs tend to be fire and forget. I generate some code and then, I may decide to do something later, but I won't really look at what it did. And I think there's a lot we could learn from that dynamically.
When you do the tracing, did you do a ring buffer? Did you do
the processor tracing? Yeah, it's a ring buffer. And you can choose. It will tell you if it's overrun the buffer or not, and it's an arbitrary size one in memory.
But in your loop thing, right? You you interpret, then silver trace, then you decide whether you want to compile to a machine code. In that case, how many instructions are you looking at?
It depends entirely on the size of the loop. Some are tiny, some are very big. Typically in these systems, you say if the loop is too big, you just discount it after a while because you assume something's gone a little bit wrong. I'm happy. Maybe worth going over that one in detail. Because I'm aware that you guys have got other things to go to. But I'm happy to talk about that in as much detail as you'd like offline.
Well, me too.
Thank you very much for all your questions.